Today I'm going head to head with AI in a live Java coding battle. 3 rounds, an algorithm problem, a concurrency bug, and a real backend feature. Same prompts, let's see how the AI compares to a human engineer. On the left is OpenAI Codex, on the right is my Java IDE. We're solving the exact same problems. Round 1. An LRU cache, or a least recently used cache. An LRU cache is a memory structure that keeps the most recently used data and evicts old entries. You see this in browsers, databases, and backend services to speed up repeated requests. The challenge is doing all of this in constant time. So let me put this prompt into AI and see what solution it comes up with. But my solution, I'm using a linked hash map in Java, which is a built-in data structure which already supports LRU behavior. That lets me write less code and reduce bugs. Here is my implementation on the right. And here on the left, you can see the AI implementation. The AI built the classic textbook version, a hash map plus a doubly linked list. I'd usually prefer the standard library solution, but in real Java code, it's simpler and easier to maintain the linked hash map. So this round is basically a tie, different engineering styles. I would give myself a slight edge for using the inbuilt Java data structure. Round 2, concurrency bug. So again, let me put the prompt into AI and see what it comes up with. And let me also analyze the issue. So this program increments a shared counter using multiple threads. In real systems, this shows up in metrics, balances, and background jobs. The tricky part is making sure threads don't corrupt shared state. Here, the balance here is the shared variable, and we've got 1,000 tasks that we're submitting to add money, which is incrementing this variable. We've got an executor pool, which has 8 threads within it, and we submit 1,000 tasks to the thread pool. So the expected answer is 1,000, but let's see what it actually prints. 981, 993, 989, and so on. We basically have a concurrency bug. Because multiple threads read and write the same variable, some updates get lost. That's a race condition. So my solution to this would be, instead of using an integer, you use an atomic integer in Java, and that guarantees that the increments happen atomically, i.e. you won't have another thread reading the variable until the thread which is currently updating it has actually finished. So all updates are atomic. So the change is simply to call this an atomic integer. And I also, instead of just adding it this way, I have to call the atomic operation balance.add and get amount. Let's just see the issue here. Quiet type. Yep, I'm not setting it as 0, but a new atomic integer 0. Okay, let's see what this prints now. 1,000, 1,000, 1,000 every time. So we fixed the concurrency bug. Now let's see the solution that AI has provided. And it is actually exactly the same solution. So the AI recognized the race condition immediately and used the same atomic approach. That's exactly what we want to see. I would say that's a very strong performance from the AI. Round 3, a rate limiter. So again, let's put the prompt into AI and see what it does. And I will also be analyzing the problem. So for each user, we want to keep timestamps of recent requests and remove the old timestamps, and we also check whether we're over the limit. Here is my solution. Basically, we have a concurrent hash map, which the concurrent hash map deals with the concurrency issues within the hash map because we're storing it per user. So the key is the user ID. and we then store a deck, which is a queue of timestamp values. And in the allow method, this is also a key thing, that even though the concurrent hash map handled the concurrency within the hash map key for each bucket of the hash map, but there's the actual structure, the queue structure, which is also a separate structure in the heap memory. So you have to also be careful to have synchronization on that as well. So this is basically the solution. You have a concurrent hash map with a string to handle this per user, and then you have the deck as the value. Just to show you how this works, so we instantiate a rate limiter with a maximum of 2 requests, let's say, and a window of 1000 milliseconds. Now we expect the first 2 requests to get through successfully, and the third request for the same user to be blocked. Now if I was to change this to a different user, that will be allowed, because you're allowed 2 requests per user within the 1000 millisecond window. So that's working as expected. Let's see what AI has come up with. So it's actually come up with the same concurrent map, and it's got a user window instead of the deck which I had. And what is the, let's see how it's defined, what the user window is. The user window is basically also a deck. So this is actually a very similar design. It's handled per user tracking, and it's also got the synchronized block here. So it's handled thread safety correctly as well. Another solid result. Now the final verdict, you can see that the AI is incredibly fast and generates strong baseline solutions, but engineering is about judgment and choosing the right abstractions and writing maintainable code. The real advantage comes from combining human reasoning with AI speed. If you want a harder rematch, comment what I should build next. Thanks for watching.